Hi everyone, and welcome to this fourth and final lecture with Jan Manschot. Please remember the lecture notes and videos will be on the website. And if you have any question during this talk, please raise your hand and I will leave you with Jan. Please go ahead.
Thank you, Daniel, and also welcome to this last lecture. Yeah, please feel free to interrupt if you have any questions. Happy to take those into account. Are there any questions at the moment? So maybe let's recap a little bit about the lecture from yesterday. We started to look at the path integral of the topologically twisted partition function with specific attention to this contribution phi from the U-plane integral for observable O, which can itself be a product of observables. We have seen that on the right-hand side, then the full infinite dimensional path integral reduces to a finite dimensional integral over 0 modes, the modes A and A bar from the parameter phi, auxiliary field capital D, and then fermions eta and chi. Since we are assuming that the manifold is simply connected, there are no 0 modes for the one form fermion field psi. Then the integrand of the path integral takes the form of a few terms which are topological terms, coupling to the Euler number and the signature of the four-manifold X. Then the 0 mode Lagrangian, where we can omit most of the terms with derivatives and the observable. Okay, we have massaged this integral quite a bit to the sum over fluxes of the U1 fluxes of the unbroken Gates group reduced to this form of a Siegel-Noreen theta series. Here we have the exponents. Q is e to the 2 pi I tau, Q bar the complex conjugate, and we decompose the flux to the positive and negative definite sublattice. And in this case, we have B2 plus is 1, so we just have a single direction for the positive definite lattice. And then we have this extra term multiplying the exponential terms and an extra sign. So then the integral takes this form. Integral, we've changed variables to tau. We get an integral over this fundamental domain for congruent subgroup gamma 0, 4. Measures the tau with the tau bar. We get a function mu of tau, which is holomorphic in tau, and then this Siegel-Noreen theta series for the sum over U1 fluxes and the observable O. And this is the expression then for nu of tau with the couplings to the curvature and one Jacobian factor for the change of variables. Okay, we discussed how to evaluate this using the Mock modular forms, and the final answer, how it produces results from Goetz-Ellingrud in the literature from algebraic geometry. We've also discussed if B2x, so this was all for the manifold for the complex projective plane where B2 is equal to 1. We've also discussed if B2 of x is larger than 1. Then we can also evaluate it. I didn't go into much details, but one thing which we did discuss is the wall crossing. If we consider the difference of the U-plane integrals for a Kähler form J and the Kähler form J prime, or period point, more generally a period point J and a period point J prime, then this is evaluated in terms of these functions known as indefinite theta series. So we've discussed the relation to Seiberg-Witten invariants and their wall crossing. We have discussed that the Seiberg-Witten contributions at the singularities can be expressed in terms of these universal functions. And then in the end of the lecture, we came to the hypermultiplets. So the first bit was all about just the theory with the vector multiplet. and then topologically twisted. Okay, so the hypermultiplets, we had some interesting phenomena since, in contrast to the vector multiplet, if we topologically twist the scalars of the hypermultiplet, then these scalars they become spinors themselves, which we wanted to avoid, because we want to formulate the theories on a general Four-Manifold. So once these are spinors, we have to do something to define them on the Four-Manifold, namely by coupling to an appropriate line bundle or spin C structure, such that these spinors become well defined. You could say that the spinor bundle is not well defined on the Four-Manifold. Now we're going to couple to a specific line bundle, which is also not quite well defined, but precisely in such a way that if we multiply the two, then the product is well defined. So we've seen this for two cases. One case is for the adjoint representation. Then we arrive at the theory known as n equals 2 star. It's a deformation of the of n equals 4, massive deformation of n equals 4. And then we couple to a spin C structure denoted by CUV, which needs to satisfy this integrality condition equal to W2x modulo 2 times the lattice. And for the fundamental representation, we get a slightly different quantization condition, namely that it is W2 of P plus W2 of X modulo 2L for the fundamental representation. Okay. Now our moduli spaces are also a bit also changed in this context. We are not just looking at the moduli space of instantons f plus equal to 0, but now we have a second term in this equation, which is bilinear in the monopole fields M bar and M. And these spinors also satisfy the Dirac equation. I've just used here the spinorial notation, but again, on a non-spin manifold, we need to apply this, couple them to a non-trivial background flux. And we call now the moduli spaces of these solutions, we denote them by M, Q, K, Cj, or CUV. Okay. Okay. CUV for the adjoint hypermultiplet. K is still the instanton number, and here these are the fluxes of the flavor bundles. Q is just to indicate that these Q fixed equations. Okay, so that's basically where we left it yesterday. Are there any questions before I continue with new material? Okay, so lecture 4. So the first thing is, first bit is a little bit technical, and there are things which still remain to be understood. It is namely with respect to localization in this moduli space MQ. We have a flavor symmetry U1 to the NF, assuming that the different masses for the hypermultiplets are different. We can simply rotate these monopole fields or spinors MJ to e to the I alpha, by a phase, e to the I alpha mj. And so we can look at the fixed point locus of this symmetry. Okay, so one fixed point locus is clearly when mj is equal to 0, then this term vanishes, and these equations are automatically satisfied. So then we are just back to the usual instanton equation, and that's what we call the instanton branch. And then there is a more complicated monopole branch, where this phase is cancelled by acting with a Gates symmetry. Then we have a reducible connection. Reducible connection A mu. So this is the SU2 connection. Take the form of A mu U1 minus A mu U1. And then for the adjoint representation, we would have an upper triangular. M is upper triangular. And for the fundamental representation, we would have that M takes the form of M1, and the second component is equal to 0. And so these configurations where we have a non-vanishing monopole field or this spinner, they are known as the monopole branch. Sorry, I didn't write down monopole branch so far. Oh. Okay. So if we consider first, we'll mostly consider the instanton branch. Even though these fields are set to 0, they will still induce a bundle over the moduli space of instantons. So the hypers give rise to a matter or index bundle. Or index bundle. WK, and if we have multiple of hype multiplets, we have a number of these index bundles over MK. And we can calculate the rank of these bundles. This is then the index of the Dirac operator. Is equal to minus 4k plus 3 CUV squared minus sigma over 4. And for the fundamental representation, we have the rank of WK is equal to minus, let's do this for NF multiplets minus NFK plus 1/4 sum over J is 1 to NF Cj squared minus sigma. Okay, and the rank of these bundles precisely account for the difference of the dimension of MQ and the moduli space of instantons. So this is the real dimension, and we see precisely this difference between the dimension of the moduli space of instantons and MQ. Also here for the dimension of in the case of the adjoint representation. And now if we evaluate an observable O, then from this perspective, the path integral takes the following form. We get a sum over the instanton numbers, and then we get power of the scale of the theory to the power of the dimension of MQ. And then this multiplies, we get an integral over MQK times an Euler number of first of a bundle W tilde K times the differential form omega O0. You can think of this as the okay, let me not go into those details, but now the idea is that we localize and then we get a sum over K lambda Eden MQK m to the minus the rank of the index bundle WK times the sum from LS0 to the rank of WK times an integral over the moduli space of instantons. We get equivariant Chern classes times omega 0 plus an integral over the monopole component times equivariant Chern classes over this component m to the L omega O. And this goes back to work by Witte 94 for the adjoint paper Losev, Nekrasov, Shatashvili from 97. Also Pitts 3 Kurtz, Urine 95. And in my more recent paper, we studied this for including the background fluxes for n equals 2 star 21, and then I have papers with Asman, Fur, and myself from 2021, 22. Okay, so just some references where you could read up on these type of localizations. So we apply the localize with respect to the flavor symmetry in these moduli spaces of the non-abelian Seiberg-Witten equations. I should also point out this scale lambda if you have a n equals 2 star theory is a deformation of a conformal theory, the n equals 2 4 theory. Then we don't have a scale, but lambda is then replaced by QV, a UV parameter, dimensionless UV coupling constant. Or the adjoint representation, lambda to the power the virtual dimension of MQK is replaced by the UV coupling parameter QUV to the power K. It's dependence on the UV coupling constant tau UV. So we get an interesting interplay in that case. I will elaborate a bit on it, that we have both a UV coupling constant tau UV, and then there is an effective coupling constant tau, which is integrated out. So yeah, in this case, for the adjoint representation, the partition function then takes the following form: set of tau comes a sum over instanton numbers k times Euler numbers of MIK QK UV, because these Chern classes now becomes the Chern class of the tangent bundle of the moduli space. And there's another term which is, it's not quite an Euler number, but I will just denote it with the same notation. But we get numbers, and this is then on the monopole branch. The precise definition here is more subtle. Is more involved. And I would refer to the papers by Thomas, Tanaka, and Thomas from 2018, maybe, on Waffa-Witten theory. Okay, are there any questions on this side? Okay, so there are many questions here, precisely how to do this localization and to define these invariants, especially if your moduli space has singularities. You have to do something special for to define the precise cohomology theory. Yesterday we discussed a bit that this was the standard cohomology or Dolbeau cohomology in a complex case. But if there are singularities, you might need to go to more abstract cohomology theory. So I won't go in too much detail here, but I will proceed with the technique of the low energy effective field theory. Since we have seen already yesterday for the vector multiplet that it's a powerful approach, we can do calculations there, even though it's not so clear what we are actually calculating, but we can do the calculations and then in the end match with results in mathematics, which puts both sides on a firmer footing. So I will first discuss n equals 2 star. Similar to the pure case without the hypermultiplets, there is a Seiberg-Witten solution. I won't describe the curve in detail, but the solution gives us now an exact expression for U tau UV. So as I said, we have an effective coupling constant tau, low energy effective coupling constant, and we have a UV coupling constant we introduced from the outset. It's intriguing that this is now an example of a bimodular form because it transforms under modular transformations under both these parameters. And we have that if we let tau go tau UV, then U diverges. We get to the following perspective then for the U plane. We have draw the U plane. So for tau going to tau uv, we go to infinity. Then we have let me just say this the U plane. Then we have two singularities which are similar to before, where a monopole and a dion becomes massless. And we have one extra singularity where the hypermultiplet becomes massless. Okay, so when this if we add this hypermultiplet, and now we get an extra singularity in this moduli space of the U plane where the hypermultiplet becomes massless. You can also see this from the perspective of the curve, that there's an extra singularity where the curve pinches. Okay, we can change variables again, much like in the pure case, to a domain in the fundamental domain in the upper half plane. I'm drawing the upper half plane. This is a gamma 2 fundamental domain. Takes the following form. Again, this side is identified with this side with the arc here, and this arc with this arc. This is a congruence subgroup gamma 2, where the matrices of this subgroup are equal to the diagonal matrix, identity matrix 1, 0, 0, 1, and then modulo even, that matrix modulo even integers. So now we see we have again these strong coupling singularities here, which map to the monopole and the dion singularity. And this boundary here at infinity, that is around tau uv. So you have a point tau uv with a boundary around it. That's the boundary here. And then the hyper singularity corresponds where we send tau to I infinity. So that's maybe I'll put it a little higher. That's the boundary there. That's the identification between the domain in the upper half plane and the U plane, and we see these different points. It's really a gamma 2 fundamental domain, but the special thing is that we have this extra singularity in the interior determined by tau uv. Okay. And we can evaluate the U-plane integral. The U-plane integral in this case again depends on this second Stiefel-Whitney class or first term class of the Gates bundle. It depends on the period point J. As we discussed, it depends on CUV, and it depends on tau UV. We are integrating over tau, just as I was reviewing there at the beginning of the lecture. So the final integral is depending on these parameters. And this is done in some detail in the paper with Craig Moore I was citing from 2021. So how do we do this? We weekly gates. Let me add a couple comments how this is how this coupling to the UV spin structure happens in the low energy effective field theory. We so-called weekly gates the U1B vector, the U1B symmetry. We call it here it's the flavor symmetry or baryon symmetry. By introducing a so-called frozen vector multiplet. Frozen vector multiplet such that the field strength of this vector multiplet FB over 2 pi is equal to CUV. The scalar field of this multiplet is AB is equal to the mass of the hired multiplet. And we have then these fermionic fields chi B, and eta B are set to 0. These fields are not dynamical, but just specify their fixed values, and the parameter is then in the Lagrangian. And then we have the low energy. The couplings in the low energy effective field theory are determined by the prepotential. FAM. For example, by these derivatives, second derivative of F to A and M. And this is then, sorry, this is the curly F, the prepotential. This is then multiplying the U1 field strength F, multiplying the field strength of the vector multiplet FB. And we have similarly a coupling, a second derivative of the prepotential F to M squared, and this multiplies then the FB squared, etc. Okay. Any questions so far? Okay, so yeah, I won't go into too much detail of setting up the integral, etc. I've shown it yesterday for the pure theory, and we're going to look into the papers at the concrete details. One interesting aspect I find is that if we choose the canonical spin C structure, on an almost complex surface, then we reproduce many results of Waffa-Witten theory. Which is then a confirmation that of this idea that the moduli spaces, the moduli space for the adjoint non-abelian Syrah-Witten equation is a compact deformation of the other equation of the Waffa-Witten equations, and that therefore the invariants or correlators are actually the same. In particular, for B2 plus is 1, the case of CP2, complex projective plane. We reproduce results of class numbers, which appeared in the context of Waffa-Witten theory. So we had expression like this. Okay, B2 is equal to 1 divided by the eta function to the power 6th times the sum over integers, possibly half shifted. And then we have arithmetic numbers known as the class numbers, 8s of 4n, q to the power n uv. And this function is an example of a mock modular form, like we were discussing yesterday. And so we derive the mock modular form together with the completion from the path integral of the n equals 2 star theory. So the completion, non-holomorphic completion, reads 3i over 4 square root of 2 pi times the integral from minus tau bar uv to I infinity times the theta function, basic theta function, divided by minus I tau plus u to the 3 over 2 times du. Okay, and this is, should refer to this, was these basically these numbers were derived by Kliachko and Yoshioka, and then also developed by Rafa-Witten to verify the S-duality conjecture for n equals 4 Young-Mills. That all nicely fits together. This total non-holomorphic partition function is now transforms as a modular form, and it is crucial to have this non-holomorphic part in addition to the holomorphic generating function of the Euler numbers of the modular spaces of instantons. Okay, are there any questions here? Okay, I'll continue then. We also derived universal functions for the Seiberg-Witten contributions. When B2 plus is larger than 1. These were these functions A, curly B, curly C. And I had yesterday on the slides also. In this case, they depend on tau uv. So there's again this interesting connection with modular forms. Just as an example, AJ can be expressed as this ratio of eta functions. And then we have other examples for other universal functions. And this can be matched then with also results by Dijkgraaf, Park, and Fecha and Cole. And we also mentioned then that in the decoupling limit m to infinity, we reproduce results for an f of 0. Okay, any questions so far? Okay, maybe as another comment, this CUV, the CUV has been recently understood also in within algebraic geometry as giving rise to twisted Rafa-Witten invariants, L-twisted Rafa-Witten invariants. Okay, any questions? Okay, so no questions. I want to continue with describing some results for fundamental hypers. In this case, we have a scale which I want to distinguish between the different theories. So I give it a subscript NF. So these are also quite intricate to study. One comment is that the fundamental domains are not so straightforward as we have seen so far. They start to include branch cuts and branch points. The fundamental domains involve branch points and cuts, and depend on the masses mj on mj. If you would like to see more details, I can find in the paper AFM with Johannes Asman and Elias Ver in 2022. And in particular, then if you take the Mars is very large or very small, you see quite different domains. If you choose your masses to be, you see that they asymptote to the result of the NF is 0. So you get a nice. So you see how the domains evolve from one theory to another theory if you take the decoupling limit. So again, we observe instanton and monopole branches. And the correlation functions correspond mathematically to so-called Segre numbers. The contribution from the instanton branch correspond mathematically to Segre numbers. As studied, for example, by Gutsche and Cole in their work from 22. So maybe just to indicate their that setting, then they consider generating functions sum over the instanton numbers. They have a generating variable z with exponent the virtual dimension of the instanton moduli space. Then they have an integral over the moduli space of instantons, or a more algebraic version. The integrated Chern class of a bundle over MK. That's our to be identified with our index bundle. And they can also insert observables associated to points and surfaces cycles on X. We can identify them with partition functions on the physics side. With partition functions in physics. Then we come to the following, namely that Z is equal to lambda 0 squared over 2m squared, where the scale of the NF is 0 theory is related to NF lambda NF as follows, and to the NF lambda NF 4 minus NF. And the mass is here, the equal mass case. So M is equal to MJ for all J. Okay, then we crush it. And in this way, we can determine then invariance for P2. The basic example. And for this manifold, actually, the monopole branches are absent because of the Seiberg-Witten invariance, Venice, and just to give you an example for an FS2 and the correlator U squared, we find an example like this: 19 over 2 to the 6th and to the 4 plus 23, 2 to the 7, lambda 2 squared, m squared plus 53, 2 to the 18, lambda 2 to the 4. So this nicely matches with the predicted result, the predicted form of these numbers, and the leading term, if you take the mass to infinity, these terms will be suppressed. This will be the leading term, corresponds with the NF0 result. This was for Cj is equal to 0. We can also include non-vanishing background fluxes, and we get then different numbers. We can also, for B2 plus is 1, for B2 plus larger 1, there is a monopole branch for which we can find contributions, and we can reproduce these universal functions. Reproduce universal functions. This is mostly work in progress. We had some preliminary results in one of the published papers. And an interesting aspect is that we have find contributions from the monopole branch, which are new to mathematicians. Okay, so let me expand a little bit on this. That we find in a specific case when mu is 0, and f is 1. We find that the total partition function then Z0 is a sum of the instanton branch plus the monopole branch. As a very simple result, it just comes out as 64 m squared over lambda 1 squared. Whereas the contribution from the instanton branch is an algebraic function, and if we expand it for large mass, we get an infinite series in lambda 1 to the 4 and to the 4 minus 5 over 16, lambda 1 to the 7 and to the 7, and then further terms. So it's nice that we find this more generally, that the total partition function comes out as a rational function, whereas the individual contributions to the monopole and instanton branches are rather involved algebraic functions, but they sum up precisely in such a way that the end result is just an algebraic function here. In this case, it's even just a monomial. So there's again an interplay between the monopole and the instanton branch. You could see this as a bit similar to the n equals 2 star case. There was an interplay at the level of modularity, that instanton and monopole branches, they transform into each other using modular transformations. Here it's not. Here we still see some interplay. There are of course no modular forms around anymore after we integrate over the effective coupling. Okay, are there any questions at this point? I think it might be a good point to pause. Then after the break, I'll continue to discuss so-called connections to K-theoretic Donaldson invariants, for which we will study a 5-dimensional theory compactified on X times S1. So it'll be slightly different setting. So I think this will be a good time to take a break. Okay, welcome back for this last hour. Are there any questions about the previous hour? Okay, so we'll continue in this last hour to describe the connection to so-called K-theoretic invariants. and 5-dimensional theories. So this is reporting then on a project with Hyun Kim, myself, Moore, Tao, and Zheng. It came out, I think it was September last fall. So what? Just to start with the generating function, maybe as considered on the math side. Again, we consider a four-manifold X. Now, as a generating variable, we use a curly R. I will explain the physics relating to physics in a second. On the right-hand side, as we have seen before, we get a sum over the instanton numbers k. So the R is the generating variable, so we get a power R to the 4k, and then the coefficients in this expansion are the indices of the Dirac index, possibly coupled to some bundle over the moduli space of instantons. Okay, so it's good maybe to get this clear. Earlier we were looking at the Dirac equation for spinors on the manifold X. Now we are looking at the Dirac index of the Dirac equation on the moduli space of instantons Mk. Okay, and we are aiming to determine the index of this Dirac operator. And this is how it relates to k-theoretic invariance, that these indices are formal differences, and they are also then known as k-theoretic invariance. But if you're more familiar with indices of Dirac operators, just think of it this way, as the index of the Dirac operator on the moduli space of instantons. Index of in algebraic geometry, people will study a slightly different but closely related generating function. I will denote it by Z tilde. X R is the sum over is the numbers k, and now we summing over the holomorphic Euler characters of Mk R to the 4k. Okay, I mean, people maybe who know about index theory know that these are related, that the index density for the Dirac operator is related to the index density for the holomorphic Euler character by just one exponential factor relating the A roof genus to the tot genus. So this is the A hat versus tot class in the index density. Okay, any questions here? Okay, so again, in the following, I will take the approach of low energy effective field theory, setting up the low energy effective field theory on the Coulomb branch. Again, that theory doesn't really seem to know what it is calculating, but still we can carry out the calculations and deduce interesting results for these quantities in the in the ultraviolet perspective. So we'll consider n equals 1 super young males on x times S1. That really has the same supersymmetries as n equals 2 in 4D, but now we are in 5D, so it is n equals 1 super young males. Let us recall a few aspects of the interested theory. These theories go back. They were studied by Seiberg in '96, and then many works followed. So these papers, these theories consist of a vector multiplet with bosonic fields mu sigma. They depend on a 5D Gates coupling. I know it was G5D. G5D. It has dimensions. It's a G5D squared has dimension of length. And it has global symmetries. It has an SU2R group. The same group fits in n equals to 2 4D rotates supersymmetries among each other. And there is now a new phenomena of a U1 group. Even so, we just consider the vector multiplet. We don't include any hypermultiplets. Yet this theory with just the vector multiplet has an additional global symmetry, which is the U1, noted as the U1I symmetry, for which the current is the instanton density. So the current for JI is the star of trace of F, which F. In addition, there's a Kaluza-Klein symmetry from the circle, U1KK. Sorry, Kaluza-Klein. But this we won't play much of a role in the story here. Again, a bit similar to what we did before, we will weakly gauge this U1I symmetry, just like as we were gauging the flavor symmetry in the 4D theories. So this gives us then an extra field strength. And scalar field. A non-dynamical or frozen vector multiplet with bosonic fields. AIM sigma I, M running from 1 to 5, the spacetime indices. And now in 5D, we have a bit more, there are a bit more possibilities to write down actions for this theory. In particular, we can write down Chern-Simons couplings, and one which will be particular of interest to us is the so-called mixed Chern-Simons form, mixed Chern-Simons coupling, which is a combination of the field strength. So I'll just think of being now in flat space. R5. We can have a mixed coupling where we have the field strength of this non-dynamical vector multiplet, and this is multiplied by the standard three-dimensional Chern-Simons terms to get a 5-to-5 form. ADA plus 2/3 A cubed plus 1/8 pi squared sigma I trace f wedge star f. So this is if we supersymmetrize this term, we get other terms, and even though this term is topological, other terms are not necessarily topological. And so we get this expression of sigma I multiplying trace f wedge star f, and then there are further terms also involving the fermions. An interesting aspect is that this is really the kinetic term for the SU2 field strength. It's multiplied by the scalar, but if we give it the standard, we can choose this scalar of this global symmetry vector multiplet, such that this really the standard kinetic term in 5D. We choose sigma I is equal to 8 pi squared over G 5D squared. Then this term is the standard kinetic term for the Gates field. Term. Okay, so it's interesting that this, if we start with this mixed Chern-Simons term, then we can get the standard Lagrangian with the standard kinetic field. So in that sense, we don't have to add the standard Lagrangian with the kinetic term in addition to this mixed Chern-Simons term. If we choose the coupling like this, it's an interesting. I find it an interesting aspect. And also we see directly how then Fi couples to the dynamical field strength. Now we compactify on S1. On a circle of radius r, and then the complex scalar phi we saw in 4D arises as follows. It's the scalar field sigma of the vector multiplet in 5D plus the holonomy of the Gates field around the circle, I divided by r, integral over the circle as 1 am dx dx. And then we introduce the dimensionless parameter. That's our curly r. Curly r. It's this radius r to the 4 times lambda to the 4, and this is equal to e to the minus 8 pi squared r over G 5D squared plus I times the holonomy of the Gates potential for the background vector multiplet. So this is how these parameters are related. Okay, any questions so far? Okay, so yeah, we perform a partial topological twist with respect to SU2, the SU2R symmetry group here. Just twisting the four-manifold part and not the circle. Partial topological twist on X. So this means that the observables will be topological on X, but they are not topological on S1, and therefore they do depend on the radius. Observables are independent of the metric on X, but do depend on the radius R. And that's what we see in these generating functions, that they do depend on R for this curly R. Right down here. Okay, any questions? Okay, now we can do pretty much two things. We can either compactify on S1, make S1 very small and get a theory on X, or we can make X very small and consider a theory on S1. First, comment a bit on the second option, and then continue with the first. So the second option, if we get a theory on S1, we get collective coordinates. So we perturb around a classical solution, AX, AX plus delta, say J, or maybe not a good name, delta IA, where I runs over all the directions in the moduli space of instantons. In the ASD equations. And similarly for fermions. And then we get a supersymmetric quantum mechanical theory with target space MK. So for each instanton number, in the sense, you would get a different quantum mechanical theory. And the partition function of this quantum mechanical theory gives us the Witten index. Trace over the Hilbert space, -1 to the F, e to the minus beta h, which then evaluates to the index of the Dirac operator on MK. Okay, any questions? There is important note to comment to make, namely that the Dirac operator is not well defined if MK is not spin. We get into the same aspects that MK needs to be spin in order to define the Dirac operator, and therefore the index is also not well defined. Particular the sign of the Pfaffian of D is ill defined if MK is not spin. Okay, any And basically from the other perspective of compactifying first on X, I'll comment a bit more there. We came to the idea that there is a topological condition which determines if the moduli space MK is spin or not. That this topological condition is the intersection pairing of the second Stiefel-Whitney class of the Gates bundle with the second Stiefel-Whitney class of X. This has to be 0 modulo 2. If this is satisfied, then MK is spin. If this is not satisfied, then MK is not spin. You could also see it from the perspective of the 5D Lagrangian, or here that this sign of the mixture in Simon's form is not well defined under Gates transformations if this condition is not satisfied. So there's an interesting interplay between either this moduli space of instantons being spin or not, and more macroscopic quantities. Now it is possible to cancel the anomaly. If this is odd, there is an if this pairing is odd, there is an anomaly. We can cancel the anomaly if this is odd. Cancelled if this pairing is odd. By turning a flux for this this U1I symmetry. By including a flux for U1I. And then the condition is B W2P W2X plus Ni is equal to 0 modulo 2. Ni is equal to 1 over 2 pi and the class of the this U1I instanton symmetry. So if we turn on this flux, this will induce also a bundle over the moduli space of instantons. In particular, it will induce then the appropriate spin C structure in order to have a well-defined that's so that our fields are well-defined, even if MK is not spin itself. Okay. Okay, then we continue with the four-dimensional perspective. If we first, if we compactify on S, making S small and considering X big, but still keeping the full Kaluza-Klein tower of the circle. Now the order parameter is not just the trace of phi squared, but the order parameter in this case is the Wilson line. The Wilson line compactified, or the Wilson line for a contour around the circle. The order and on one branch is the Wilson line. Is the trace in the fundamental representation of the path ordered product of the integral over S1 sigma plus IA5 dx5. This expectation value we denote by capital U to distinguish it from the little u of the U-plane in 4 dimensions. You can do a semi-classical analysis to see how this function behaves as function of the 4D parameters. It goes as e to the RA plus e to the minus RA. And then there are further corrections depending in a power series of curly R to the 4. Okay. So what we are seeing here is that if we take R to 0, then this will go as 2 plus RA squared, and you can actually show that you get that you get U, that you reproduce the order parameter U if you send R to 0, except for the leading term 2. But if you subtract that, then this you produce the order parameter U. Before there is a prepotential. There's a prepotential worked out by the Seiberg-Witten solution for this theory. It depends on these parameters A and then curly R, and in the same way, then we have an effective coupling or couplings, which are obtained from the prepotential. For example, tau is as usual the second derivative of f to a squared. Okay, any questions? Okay, so we can, in a sense, repeat again a bit similar steps we saw before. We can plot the capital U plane. And in this case, you will find actually 4 singularities. We get 4 singularities. I'll plot them here. There is U1 and U2. U2 is at 2 plus 2R squared. Then U1 is at 2 minus 2R squared. Then there are 2 singularities on the left-hand side, U3 and U4. U4 is equal to minus 2 minus 2R squared. And U3 is minus 2 plus 2R squared. You can think of this as 2 copies of the. You can think of it as 2 copies of the fundamental domain of the pure theory in 4 dimensions. So we get one copy here, and then there is a copy here. I'll say a little more about it later. So we have. 2 copies of the 4D small U plane. And these are related by a Z2 center symmetry. We recall there is for a Wilson line like this, there's a center symmetry where we have a symmetry where we change the gates, a connection such that this expectation value changes by a sign, and that just changes, then maps these 2 copies to each other. I'll come back to this point with a few more comments later, but let me first also then give the corresponding diagram in the upper half plane as function of the effective coupling tau. So here we get 2 copies of the fundamental domain for the pure theory. We get a copy marked like this. This is the copy with 0, 8 mod comma 0, 4. And then we get another copy adjacent. We'll plot it adjacent, but it's really another copy. So this is 2, and here we are at 4 and 6. And there's a branch point where u is equal to 0. And we can take the branch cuts then going to infinity. That's where the two copies are connected. So the usual formula to write is maybe u of tau squared is -8. Actually, there's a precise formula in terms of capital U and small u, which looks as follows: +4 r to the 4 plus 4. Okay, this is also actually quite similar to discussions of these fundamental domains for theories with 4D theories with hypermultiplets, where we also were seeing these branch points and branch cuts. Now, in this theory, we take R we consider R to be small, and then these branch points, they will move up, for R to 0, and we'll cut off this domain at the value y, which is below the branch point, to do our integrals. Okay, so this is we will then be integrating over these two domains. Okay, I already mentioned we have this electric Z2 for Z2 center symmetry. We have an electric Z2 form, or in the older literature it's known as a center symmetry because it corresponds to the center of the gauge group. We shift A by a ZG valued flat connection. In our case, it maps A to A plus pi I over R, and capital U to minus U. And there is a center symmetry anomaly in this theory. Which is also discussed by Giannolini, Tisano in 2020, and Abruzzi and others in 21. So it's that the path integral Z changes precisely by this phase, this pairing of W2P and W2S plus Ni times Z. Okay, so we can evaluate in this approach with the path integral. We actually can with the low energy effective approach, we can confirm this anomaly. We set up the U-plane integral over the capital U plane. Which depends on this flux Ni, and then on curly R, we get an integral over this domain, I denoted by Fr, these two copies of the fundamental domain, d tau, where's d tau bar. And then we have this, we get a similar function V times a coupling Cn squared times psi mu j tau bar. And in this case, we also get elliptic various due to the coupling with the U1I symmetry, which takes the form of V times N and V bar times N. All these ingredients can be worked out explicitly, and have explicit functions in terms of modular functions for these terms. Should also comment here on the work by Gutsche, Nakajima, Yoshioka for some of these couplings from 2006. And then this integral takes the form of 2 times 1 plus minus 1 b w to p w to x plus n times the constant term. So we take first we make a series expansion in R, and make a small, so that we are at small r, and then we take the coefficient of q to the 0 of these terms, mu r of tau Cn squared, and then we have a mock modular form of the forms we discussed, but now with including an elliptic variable tau and v. And now we see from these two terms here, one and this term, that's due to the two copies. Due to the two copies we saw in both the U plane and the tau plane. And also due to these copies, we see that if this is odd, if there is an anomaly, then actually the partition function vanishes, because then we have 1 minus 1. So the partition function vanishes if there is an anomaly. Okay, any questions? And this is a bit similar to the Z paper on Z2 anomaly by Witten in 82. Okay, now we can precisely do this. Yeah, we can work this out. We can go to X is P2. And then we get, for example, the following results. In this case, for the Hoofdflux, 1/2. The second Stiefel-Whitney class is odd for the Gates bundle. We get results like as follows. We get 1 for n is plus or minus 1. Power series 1 plus r to the 4 plus r to the 8, just coefficients 1 for n is plus or minus 3, 1 plus 6r to the 4, etc. for n is plus or minus 5. And for all the even numbers, we have an anomaly, but then it vanishes because of the previous previous comments I just made. And this reproduces nicely results for K-theoretic Donaldson invariants. Donaldson invariants by Gucci, Nakajima, Yoshioka. I cited here. And we can also extend them to B2 plus larger than 1 and use this ID to derive the universal functions from the U-plane integral using the wall crossing. And we also find nice agreement. We have cyber-written contributions with universal functions. In agreement with a paper by Lothar Gutsche, Cole, and Williams from 2021. Okay, so this gives us a nice kind of confirmations on both sides that things are working out very, very nicely, both in the effective field theory and in the mathematics as well as the UV perspective. Okay, so this more or less brings me to the end of my lecture, so what I wanted to explain. There are still various other theories out there which we are working on to further explore and relate to other four-manifold invariants. So thank you very much for your attention, and I'll be happy to take questions. Thank you.